Welcome back to this second part of our um, parallel programming extended lab for utilizing shared memory for calculating an image filter. In this video, I'm going to go and start writing the code here, and we're going to use the concepts we talked about in the first version, in the first part, as to how we would basically go ahead and work on the program and the indexing. So here we go. The first thing I need to do here is to set up my shared memory. So the setting of your shared memory is fairly easy. Like any other local variable, you basically create a variable. This time I'm going to create a two-dimensional array of variables, and I'm going to call them tile. And I will tag that with the keyword shared. So shared unsigned char tile. And then the size of this tile, I'm going to make it k by k. Now, look at the k here is 16, which is the size of the block. So for this version of my program, I'm going to write a program that utilizes a shared memory whose size is exactly the same size as the block itself. So to show you how it looks like, the tiled version of my program is going to bring in a block of shared memory. So for each of these blocks, here I've got a yellow block and a red block, just to show you how this operation works. So for each of these blocks, I'm going to create the shared memory the same size as the block. So for example, as you see here, these threads, I'm going to call them yellow threads. So they're all going to be yellow threads for the yellow block. And I'm going to create the shared memory the same size as the block. Now, there are two phases in my program. Phase 1 is bringing in and filling my shared memory part. So I'm going to use part 1, filling shared memory. And I'm going to use my part 2, using the shared memory. Now, as a part of calculating and filling my shared memory, the first thing I need to do is to find indices in global memory. And once I calculate the index from global memory, I can use that index with the index of my shared memory to write into shared memory index from my global memory index. Let me show you how it works. Now, each of these pixels will have an actual location in global memory, and I'm going to call this or mark them with a little black X mark. So these black X marks for each of these pixels is going to be their content that I have for each pixel in global memory. The yellow is the shared memory. So what I'm going to do is that I'm going to have each of my threads effectively read the content from global memory and write it into its own location in the shared memory. So effectively, the idea is basically for global memory to go in, for each thread, to go in and read from global memory and fit it in its location in shared memory. Now, what is the location of each pixel in shared memory? That is fairly easy. What is this location? It's actually threadIndex.x bracket threadIndex.y, because each of my threads effectively will have an index x and an index y, so its own location in shared memory is its own threadIndex.x and threadIndex.y. What is the location in my global memory? That I calculated it from the index in the previous video. That would have been its x global x plus its y times block dimension.x times grid dimension.x. Okay, and the x and y are thread index.x plus block index.x times block dimension.x. So that is my x, and same with the y. It's going to be block dimension.y times block index.y. So once I use these guys, I can calculate the index, and then from index I can fill in my shared memory locations. My shared memory locations in the shared memory. So let's go ahead and start working on the first phase of this program. So the first phase of this program is for me to go ahead and calculate the location x and location y of each thread in the shared memory. This actually turns out to be fairly simple. It's going to be the location x is going to be thread index.x, and location y is going to be thread index.y. Now that I have my shared memory locations for each thread, I'm going to have to go and calculate both the x and y location in global memory and the offset from where I'm going to read from global memory. To access that, I have x equal thread index.x plus block index.x times block dim.x, and my y will be thread index.y plus block index.y times block dim.y. Now that I have calculated the x and y locations, I need to go and calculate the offset, or rather the index. Index of my pixel in memory is going to be x plus y times grid dimension.x, that's how many blocks in x there are, times each of the block sizes. It's going to be block dim.x. This index is going to be the physical location of each pixel in memory. Now that I have the pixels in global memory, all I need to do is to go for each of these threads that is running at thread index.x and thread index.y to fill in, to bring in the content from global memory and fill in the location in shared memory. So that turns out to be fairly simple. I'm going to write in the tile L sub x and L sub y whatever the input image was, which here I call it source. So I'm going to read from source at location index. What this does is that basically it goes at location index, brings in the value of the pixel from source, and puts it at location L sub x and L sub y of my thread, which is my tile, which belongs to each thread. After I do this, I'm going to have to do a sync threads to make sure that that all threads finish reading from global memory and writing into the tile before I proceed and go in and perform my calculations. Now if I compile this program, this should work. And at this point, nothing will really happen because I haven't really performed any calculations on my image and the data so far. So if you run this program so far and press, for example, 3 to calculate the GPU, you'd notice that your GPU output with shared memory is going to be blank because the calculation that we have not performed any calculations. So we basically filled the tile and stored the value 0 into all of the indices of our destination. The next step for me is to go ahead and start working on the second phase of my program. So the second phase of my program is to use shared memory to perform my calculations. Now, remember, to calculate the filter, we have two for loops that we're going to run. And these for loops basically will go from -1 to +1, -1 to +1 for m and n, or here I call them I and j. And then what is going to happen is that I'm going to read from my image, which is the I at location x plus I and y plus j, and sum these up and divide them by 1.9, or rather divide them by 1/9, and this will be my filtered value that I will store at location x, y. So effectively what I'm doing is that, let's suppose that I'm going to be working on this pixel right here. What I'm doing is I'm going to bring in from its neighbors x minus 1 from that guy, and this guy, and this guy, and this guy, itself, and this guy, and the one below it. I'm going to sum all of these values up and then store the resulting value inside of x. So this will work actually with global memory with just one nested for loop. You will be able to calculate for each pixel the sum of all of its neighbors in a 3x3 neighborhood. So the idea here would be to do a for loop for I between -1 and +1, and then for j between -1 and +1, you basically go and add the location of your image at x plus I, comma, y plus j to the value, and then you divide this value by 1/9. And this value will be the result when you go over all of the 9 pixel calculations. However, there's a slight problem. The problem is this, that for these pixels on the boundary of my shared memory, for these pixels on the boundary of my shared memory in each block, as well as these pixels on the boundary, and all these pixels in the boundary, and all these pixels in the boundary, I will not have neighbors in the shared memory. So the neighbors of these pixels, as you see up here, are outside of the shared memory. And remember, threads in blocks cannot share their value in their shared memory with threads in other blocks. So for these guys, I would have to read my content from the global memory and then add into my program. So there's one caveat here. For these two for loops, then I'm going to have a condition. The condition is this: if neighbor is in shared memory, then value that you calculate is going to be from shared memory. Else, it's going to have to come from global memory. And this is what we're going to do. What I'm going to actually do is that I'm not going to write this part for you, because this part you will have written from your your global memory kernel, and the code will be fairly similar to global memory kernel. I'm going to write this piece for you. I'm going to show you how you can basically add the contents of your shared memory to the values that you are calculating. As a byproduct of this you will notice that when you look at the result of your image, the inner around each block you're going to get black values, because these I'm going to skip them in my calculation. So your calculation effectively is going to work for inner pixels because of the if statement that we have up there. Because of this if statement, it's going to only calculate the pixel values for the inner pixels of my shared memory. And you basically have to treat the pixels that are on the boundary of your shared memory independently and separately. So let's see how we can do that. I'm going to go into my program. And first thing, I evaluated or put the value sum equals 0 in each thread. Then each thread is going to go and write a for loop. So end I less than I equal negative w, I less than or equal to w. That's the size of my filter. And for int j equal negative w, j less than or equal to w, j plus plus. Now from here, what I'm going to do is, now I'm going to go ahead and calculate the location of my tile from the shared memory. So I create two temp variables. I call them temp x and temp y. Then temp x is going to be L sub x plus I, and temp y is going to be L sub y plus j. These will be temporary locations that I calculated for my neighboring pixels. Now notice that when I is negative 1 and L sub x is 0, then temp sub x is going to be negative. Same with temp sub y. Now this is what happens. If I calculate my temp sub x and temp sub y, for this pixel here, whose L sub x and L sub y are 0, for this pixel, then L sub x minus 1 and L sub y minus 1 are going to be negative 1, the temp values, right? Which means that this gives me now an idea to check to see whether a pixel has neighbors or not. So if the pixel's values are negative 1, then that means that, or the temp sub x or temp sub y are negative 1, that means that that pixel didn't have values in shared memory. And same with the outside boundaries. So for example, for this guy, my temp sub x is going to be k, because the value of my object pixel is k minus 1, the size of my block, and if I add to it, it's going to be k, which makes it fit outside of the bound of my shared memory. And this gives me that condition to test right here if that neighbor pixel belongs to shared memory. Now the test is, at this point, is going to be fairly simple. All I need to do is to check to see if pixels belong to the shared memory, then I calculate them, else I don't. So from shared memory. So here in shared memory, and for the else statement in global memory. So how are we going to do the test? The test is fairly simple. If temp sub x is negative, actually rather if temp sub x is positive and temp sub x is less than k, and temp sub y is positive and temp sub y is less than or actually equal to k, less than k, then this means that this condition ensures that neighbor pixels are in shared memory. Else, neighbor pixels are not in shared memory. So now that neighbor pixels for these guys, if temp sub x and temp sub y are between 0 and k, then I will be in the shared memory, actually greater than or equal to 0 and less than k, and greater than or equal to 0 and greater than k and less than k for the temp sub x and temp sub y. Then that ensures that that neighbor is in the shared memory, and I can use that neighbor value from temp sub x and temp sub y. And if now I won't fill this else for you. So for the else statement, you basically go ahead and write your own piece of code to add it, so that if the neighbor, if the temp sub x, temp sub y was outside of the shared memory, you basically would fill in and bring in the numbers and perform your calculations from global memory. And finally, you store the values of sum divided by 2 times w plus 1. And then you store that into the output destination. So if you program and run this code, and I'll press 3. Okay, I have a logic error in my calculation. Let me see what happened here. Okay, my error was here. This second for loop condition should be on j. So for I equal negative w, I less than or equal to wi plus plus. For j equal negative w to j less than or equal to w j plus plus, then you do the calculation of your temp x and temp y. This is basically your neighbor's location, and then you see if your neighbor are in the shared memory. Indeed, you perform your calculation on shared memory, else you'd have to perform your calculations on the global memory. So let's compile and run this. This should run. There was nothing really in my logic, or I just mistakenly typed the wrong value. And voila, here is my result. Notice that for the shared memory locations, the ones that are inside the shared memory, I get my calculation right. For the ones that are outside my shared memory, you see these dark lines. These are those pixels that I skipped. So if you look back at my program, these are the else pixels that I skipped. So I'm basically making their values equal to 0. So now next step for you is to go ahead and write the correct calculation from your global memory in the else section to make this program show and work. Now let me just go ahead and increase my kernel size to something like 32, my block size. And then when I run this program, you will notice that now, as you can see here, my image is blurred inside of the blocks that have shared memory, and for the ones that are on the boundary, they are effectively, I skipped those pixels. So now your job is to finish this program up for your global memory with the shared kernel, and perform your blurring on those values. Now one of the nice things that I did here actually is that I kept the size of my filter adaptive too, so I can have like a 5 by 5 pixel kernel that basically makes my blurring even with a wider kernel. And as you see, with a 5 by 5 kernel, I've got the image blurred even more. And of course, you can see since the size of my kernel was 5, I have more pixels in the shared around the shared boundary of my image that I had to skip. And these lines, these rectangular lines around the squares, are effectively those else statements that I skipped. So so then again, one more time, going over the logic of shared memory, the idea was fairly straightforward. I created a tiled shared memory with the same size as my block. I went in for each thread, calculated the thread index X and thread index Y. That was location in the shared memory. Then I calculated global X and global Y, and then global index of the pixels in global memory. I read from global memory at location index, and each thread basically fills in the tile at location L sub X and L sub Y. Then you sync thread. Next, I created a variable called its sum equals 0. Then I go from negative of the size of my filter to the size of my filter, half width of it, on I and J. I calculate the location in the shared memory, and if the location is in the shared memory, I read from shared memory and add it to the sum. Basically, because my filter sums everything up and then divide everything by 1 over square of the size of kernel. And if the temp sub X, temp sub Y that I calculate here belongs outside of the shared memory, then I have to go and read from global memory. So here, your to-do job is to read from global memory for these pixels. And finally, you store the resulting value in the destination location of that pixel in global memory. And this will perform your calculation. I hope that this was a helpful video to show you how you can utilize shared memory to perform calculations. And of course, I would like you to do the 3 sections of your program. Perform this task in CPU. Perform this task just with the global memory in GPU, and perform this task just I showed you here with the shared memory. Of course, you have to expand this program. This is not complete yet, to finish it up, and finally to benchmark. So I would like you to also calculate the speeds at your shared memory, the speed of your non-shared memory, global memory, and the speed of your CPU code. One last thing before I finish, I would like to talk about calculating the speed on CPU. The code that I uploaded actually does have in itself calculation of the speed in CPU. Basically, I added the time.edge, which is a functionality that calculates the time of your CPU. And then what I've done here is that in code, I calculate the t-start, which is a time variable, read the clock, perform my CPU image, and then calculate the difference between the clock now and the clock when I started, and then divide it by clocks per second over 1000. That gives me millisecond results of how much it took to perform the calculations. And of course, the CPU code right now is empty, so my CPU filter shows 0. So you have to also fill the CPU filters. So fill the CPU function and functionalities. Go ahead and fill the kernel without shared memory and kernel with shared memory. Finish it up and submit your code. I hope that this video was helpful. And again, I extended the deadline until the 20th at midnight. And hopefully this will be enough time for you to catch up and to work on this project and put things together and submit them. Do not forget to write your report. Thank you for listening to this video, and I will talk to you in the next unit.